and get to this point. Okay. So I'll go from current slide there. Okay. But let me, for her benefit and for the rest of you, okay, back off for just a moment. Over the weekend, like I said, I tried to Friday get this class all out there on Blackboard. I got parts of it, but I could not get, and it's this computer, it would not, I could not load the PowerPoints onto Blackboard. And then Saturday or Sunday when I had some time at home, I did, and it worked fine. So I don't know what was going on. But anyway, I think your entire class is out there on Blackboard now. So when you go to the home page of Blackboard, you'll see the left-hand column is a bunch of blue tabs, okay? They're split up in groups of 7, 8, 9, something like that each. And the first group of tabs, about the middle one, is syllabus and book information or something like that, okay? If you click on that, you'll see the syllabus. It's now been updated, correct office hours. Hopefully everything's correct on it, okay? The next tab under that says instructor and office hours or information or something like that. So in that, you'll see my locator card. That's when I'm in class, when I'm not in class, when I'm on campus, when I'm off campus, which campus I'm on, when I'm at lunch or not at lunch, whatever. All that stuff is there for the 5 days of the week that I'm on campus. Okay? Then go down to the second grouping of blue tabs, and about the third from the bottom, I think it is, or somewhere around in there, is one that says handouts, PPTs, that's PowerPoints, and more. Okay? And in that one, you'll see the directions for the research paper, okay, that I went over in class, and this time I've updated and gotten everything correct, hopefully on that one. All the PowerPoints are now there. And, now this is the important one, the previous classes, Tuesday and Thursday of last week, are out there. The first one, Tuesday, is called syllabus. But we did a lot more than the syllabus. We did the syllabus, we did the research paper, we did locator card, we did safety, and we started chapter 14. Okay? Then, last Thursday's class, we finished chapter 14, and it'll say something like chapter 14 or something like that. Now, let me go. These are YouTube videos, okay? And what you'll see in Blackboard is a line. It's probably the first one that's there under handouts, PowerPoints, and more. Maybe research paper instructions are first, and then PHS111, Physical Science 111, YouTube videos. That's the title of it. When you click on that, you'll get a whole string of videos. I'm guessing something about like 16 or so, plus or minus, okay? Now, the ones you see at the top are from the last time I taught the course, last spring. The ones at the bottom, that's where you'll see syllabus and chapter 14. Those will be, and I may even put lab 1 on, or maybe chapters 14, 15, and lab 1, something like that. The ones at the bottom are from this term. And you might ask yourself, why do I leave the others up there? Because we're going to be doing that this term. Or is anybody on campus yesterday afternoon? You weren't? Okay, what happened? Power went off. Okay, I was teaching a class. I couldn't record. Okay, it wouldn't load. So I leave the old ones up there to make sure that I do have one new. If something messes up in the system or power or anything else, and I can't record something, I'll leave the previous one up there so you can at least have some type of continuity. They don't all fit like a glove, but they'll have most of the material there. So that's why I leave the old ones out there. Okay, but as I do the new stuff, then I'll take off the old one that I've just duplicated. Okay. Then I was able to get all the PowerPoints loaded for all the chapters we could possibly do. And let's see. Oh, yeah. I got these. These are up the front part of that handout, PowerPoint set up. The Hubble 1 through 10. Those are just beautiful pictures taken by the Hubble Space Telescope. Really incredible stuff. No captioning or anything else, just really pretty pictures. Then there's one that's also called Space Objects in Perspective. And that has some captioning on it. And that's pretty incredible when you look at that. Okay? I think that's most of what's out there. But anyway, you can do. So that's where I put things. Syllabus, one file, syllabus. Instructor information, one file, the locator card. And then handout, PowerPoints, and more. That's where everything else is. Okay. Now, the PowerPoints are there in static form, but then when you see the videos, you'll hear me talk about them while they're up there. So you've got PowerPoints there in two forms. Same thing with the research paper instruction. It's in static form, but also if you listen to that first video, you'll hear me talk about it. So it's a bit more dynamic. Now, before we get started today, here's the thing I think I forgot to tell you before, and I apologize, but you got plenty of time to make up for it. Every test that you take in this class, you can have with you a formula and equation sheet. That means anything you want to write on a piece of paper, you can have with you during the test. And I think I forgot to say that last time, did I? Sorry about that, folks. So if you want to start writing away whatever you want to put down for your first test, we do have the Chapter 14 test coming up at the end of this class today. Okay, so that then leads to where we are, where we left off. We did do Lab 1. It's called Experiment 47, Celestial Coordinates. We did this last time, except we did not get question 14 done. We just didn't have time to do it. So we'll do question 14 today. Any who just got the labs, and I know there's 3 of you just got copies of labs, you can go back and watch the video from last time, and I think you can probably pick up most of what you need for the labs to fill in the blanks there. Okay? If not, maybe get with a friend, a neighbor, a partner, or something like that. It is a lab, so you can share data and information. Labs are open and you work with each other. The test coming up later, that's not a lab, okay? So you do those individually. By yourself. Huh?
Use a pen on the test.
You can use a pen if you'd like. It's fine with me. I tend to make errors, so I usually use pencil, but that's me. You can use whatever you'd like.
Can I ask one more question about the sheet, the equation sheet and fact sheet?
Yeah.
So anything that you can fit on one piece of paper?
Anything you can put on one piece of paper, yeah. Doesn't have to be an equation. I just call it formula and equation sheets because I teach a lot of math classes, but yeah. Uh-oh.
It said 7% and then...
Okay. Now, it was up there before, wasn't it?
Yeah, it said reserve.
Okay. What happened, I think my book hit my plug-in and it knocked it loose. It's locking my computer. Thank you very much for doing that. I don't know why. All right. I think this is where we left off, wasn't it? Good. Thank you for catching that. All right. Any questions before we get going on question 14 on your it's page 366 of the lab? All right. It says we don't have a celestial globe, but what we're using is a drawing. So I'm going to do the drawing here. Okay. We're going to set up ourselves to be on the globe. That's a pretty ugly globe. Here we stand, Bessemer, Alabama. Okay. Anyone remember what our latitude is? It's what? 33 degrees, 23 minutes, 45 seconds. That's our latitude here in Bessemer, Alabama, approximately, okay? Here's our horizon. Here's the south horizon. Here's the north horizon. Here's our celestial sphere, or hemisphere. Directly above us is our what? I wrote a Z there. What does that stand for? Zenith. That's our zenith. Okay? That's directly above us. Okay? Now, just about a third of this distance here is the celestial equator, which makes this angle here to be what? Anybody? No? No, that was the sort of standard. That was our celestial thing we were dealing with. This is our latitude. See, that parallels this. So this is 33 degrees, 23 minutes, 45 seconds. Okay. Can you catch your name, please? Maurice? Okay. All right. Our head is somewhere here. Okay. There we go. Got it. All right. So we're just missing Chris from page 1, Edward, and Ken from page 2. Is that right? Good attendance, class. Way to go. All right. Now, we're finishing up lab 1, which is question 14 on page 366 of the lab. Do you have your lab? Okay. This is the last question we had to do. And I'm setting it up here. It says, readjust your celestial globe, which is my little celestial sphere here, for my latitude, which is 33, 23, 45. And it says, what range of declinations can stars have so that they never set? That is, they're always above the horizon. Now, declination is measured from where? From what? Okay, no, that's right ascension. These terms are somewhat similar, but don't get worried if you're getting them confused. I do sometimes, okay. But what is declination measured from? No, the celestial equator. Yeah, it's the celestial equator, okay? So what range of declinations will it take so that the stars never, what range of declinations can stars have so that they never set, that is, are always above the horizon? Can anyone name one star that's always above the horizon, that never sets? Anybody? Say again? North Star, of course. And where is it over here? How can I draw, where would I draw the North Star? Okay, to the north. Okay, good. We were in the right direction here. Huh? Where to the north? Oh, don't you remember our first question, the very first question on the lab? The second? Okay, not 40. Our latitude. Okay, you're looking at question 2. Question 1, the one that's a diagram. Call alpha. Remember? No, it wasn't call alpha. Find alpha. Our latitude. The North Star is exactly our latitude. I probably didn't draw that too well. Let me try it a little bit better. I probably will make it worse now. No! Went too far, but that's okay. That's our latitude. 33 degrees, 23 minutes, 45 seconds. Okay? That's good old Polaris, the North Star. Okay? And it's not a very big star. I drew it way too big. Okay? Kind of a small star. Okay? Now, declination would be how far above the celestial equator. What would be the declination of the North Star? What's the declination of the North Star? The angle above the celestial equator. What's the angle here? 90 degrees, exactly. The equator and the North Pole, 90 degrees from each other, right? So the celestial equator, North Star, 90 degrees. So the stars that would never set would be these that are close to the North Star, traveling anywhere in that range. Okay? Now, if this is 33, 23, 45 above the northern horizon, that means they go back 33, 23, 45 on that side of the North Star. These would be the ones that circle around the North Star and never set. So what we have to do is subtract this 33 degrees, 23 minutes, 45 seconds from, what did you say that was? 90 degrees. But rather than subtracting from 90, let's subtract it from 89 degrees, 59 minutes, and 60 seconds. Isn't that 90 degrees? So 60 seconds makes 1 minute. That makes that 60 minutes. 60 minutes makes 1 degree. So that makes that 90. It makes the subtraction way easier, and you don't have to borrow 60s, or anything like that. Okay, so let's do our subtraction. What do we get? 56 degrees, 36 minutes, and 15 seconds. Okay, so the question is, what range of declinations can stars have so that they never set from here to there? That's 56 degrees, 36 minutes, 15 seconds, up to 90 degrees. That's the maximum declination. See, anything beyond here, they're the same. You're in the same space. So it's from this to 90. That's the range. Does that make sense? All right, good deal. And they'll never set. They just go around the North Pole. Any that are out here, for a few minutes of the night, they go below the horizon. Yes.
So they just go around the North Star?
Around, they look like they're going around the North Star. They're just hanging in place. We're spinning, and it makes it look like they're going around the North Star.
Oh, so
they never move. We're the one moving, but it makes it look like they move. Because we think we're stationary, don't we? We think we're special. No, we don't do that, do we? Okay. All right. All right. That finishes the lab. And hopefully most of the questions, if you weren't here to hear them in person, you can listen to the YouTube videos and get most of them. If there's any you're in doubt about, check with a friend, whatever, and see if you can put those together.
okay, the stars never move. The Earth just.
The Earth is spinning. You're absolutely right.
Oh,
Yeah, yeah. They just hang in there. You know, we're spinning. In fact, the next chapter, when we open it, we're going to talk about how much we're moving, and we are really flying. We don't ever realize it. Okay. All right. Any questions? Yes.
Oh, I to make sure I understand. So when we do celestial navigation, we do it in our terrestrial navigation and kind of compare it to the celestial, so we know where we're at. Is that kind of what's going
Yeah,
on?
exactly. And when you're doing celestial navigation, for those people who even know what that is, you're going into books and you're finding the specific time, everything is pinpointed. So when you do it, you're looking at the night sky at exactly that point. Not when it's moved a little bit, but at exactly that time, or really close to it.
That's why we got to know where our meridian is.
That's why we have to know.
So we can do that.
We have to have a really good idea where we are. Okay. But then the stars help us pinpoint. Yeah. All right. Good questions so far. Now, for those who did come in late, just in case you missed it, I neglected to say something back when I was going over the syllabus. I meant to, but I was in a rush and forgot. For every test in this class, including the final exam at the end, though you won't need it as much there, I don't think, but you can have it. You can have a formula and equation sheet. Anything you want to write down on one piece of paper, you can have with you during the test. I do not count memorization to be the goal of this class. I think it's learning the material and at least knowing where to go and look it up. So,
Is the front page of the piece of paper?
second?
One front page? Or?
No, whatever you can write on a piece of paper. Right. Okay? Now, there's a couple of reasons I do that. Number one, I said memorization is not, I think, the goal, because that's short-term memory. That's not really learning anything. And sitting and listening to me talk is not the best form of learning either. Okay? I think the best form of learning is what they call active learning, where you are planning, let me back up and do it this way. When I was an undergraduate, and some in grad school too, very seldom did I have a professor who allowed us to bring in a formula and equation sheet. But man, when I did, that night before, I was usually, when I postponed it to, I was there figuring out, organizing, figuring out what I needed to know, the important issues, the things I wanted to write down. I wanted to make sure were on that piece of paper. I was organizing, planning, writing it in places where I could see and stuff like this. And then the next day when I went to take the test, I'd sometimes forget to look at my sheet, because that I found was the best way to study for the test. Okay? So I suggest to you, every test you ever have, do your formula and equation sheet the night before. Don't use it if the professor or instructor doesn't allow it. Don't do that. That's called cheating. But to do one is active learning, because you're looking at the material, you're figuring out what you think is important, you're writing it down, which is far more active than listening to someone else talk about it. You are processing it. You're dealing with it. So I suggest you always do a formula and equation sheet. In this class, I'll let you use it, okay? But quite often, I think you'll find you may not need it. But it's the best study tool I have ever run into. If any of you have any that you think are better, let me know. I'll share that with everybody. So that's why I suggest that you use it. Okay? So, sorry I didn't say it sooner, but you got time, start jotting away. Okay. Okay, any more questions on question 14 or anything else on the lab? Okay, whenever you finish the lab, you can turn those in. You have 1 week from today to turn them in, so please get them done within that time frame if you can. If you need more time, I'll give you more time. I'm going to push over. Okay? Any questions? But don't let them pile up on you. I don't want you late in the term having half your lab still out. Get them in. Hopefully before we do the next one, though we're going to do the next one today, so you won't be able to get this one done unless you do want to turn it in today. All right. So let's go to where we left off last time. This is chapter 15. This is not on the test. This is the, before I'll, something out of order here. Let me put this aside. Okay. Okay. Chapter 15. The test is only on 14. Here's chapter 15. We're starting now to go through the planets one by one. With one exception, we're not going to do Earth. Okay? That's not a planet, it's a dwarf planet. Okay? We're not going to do Earth because the next chapter is talking about the Earth and space. So we'll talk about the Earth next time. But let's start with the innermost planet, Mercury. Okay? Yes. Say this again. Anytime you want to get rid of it. If you're afraid you'll forget to turn it in at the end of the class, I'll take it now. Okay? All right, here we go. It'll give me something to do while you're doing your test. And I might get one or two done in that call. Okay? But thank you. Okay. All right. Yes. I used to. Yes. Whether it has staples in it, I'm not sure. Oh, you don't. Look at this, the first paper of the term coming in. Actually, today I had first paper period, so that was a different class. No, thank you. Okay, did you find out? What's that? Oh, okay. Okay. Now, let me make a guess. Is it Edward? Yeah. Edward? Okay. Has anyone else come in since the called roll? So right now we're just missing Ken and Chris. Okay. Good attendance, folks. Way to go. Keep it up. All right, the innermost planet is Mercury. Now, remember Mercury has the greatest tilt to their orbit, mostly because they're closest to the sun, and just a little deviation will make a large angle. But they're also a highly elliptical orbit. Sometimes they're much closer to the sun, and sometimes they're a little further away. More elliptical than most of the others. The average distance in that elliptical orbit is about 4/10 of an astronomical unit. And we noted that in the table. And for those who weren't here, the table at the top of page 381, a great table. Properties of the planet, great one to look at. Listen to the video. I tried to point out the things I thought were pretty important. Now, 4/10 of an astronomical unit. What is an astronomical unit?
From the sun to the earth.
Say again?
Distance from the sun to the earth.
Yes, the average distance of sun to earth, about 93 million miles, whatever that is in kilometers, and it's about 4/10. So sun is here, earth is here, 4/10 would be right about there, okay, less than halfway. Now, this was one thing a little weird here. The orbital period, it takes about 3 months for Mercury to go around the sun. It's really close, so it doesn't take long for it to go around the sun. But it's a really slow spinner. Whereas we spin once a day, they spin once every 59 days. So about 2 months it takes them to turn once. So in other words, they have about, see if I can figure this right, a day and a half a year. Okay, if this is their year, 3 months, and 2 months of that is 1 day, okay, then that's about a year and a half every, no, a day and a half every year. Okay, it's rather bizarre. Okay, now, and as we saw in that last question or two, because Mercury is so close to the sun, but does have that angled orbit somewhat, most of the time when the sun, the only time you'll see Mercury is just before the sun rises, if it happens to be above the sun that day, or just after the sun sets, if it's lagging behind the sun. That's all you got. Shortly after sunset or shortly before sunrise. When they say shortly, you're probably talking about just a number of minutes, okay? And that's not very long to see a very small planet, you know, in the light that's either just around dusk. Okay? Hard to see. I'm not sure I've ever seen Mercury. Now, these two statements here are almost redundant. Highly cratered. What does that mean? Yes, you've had tons and tons and tons of impact of things hitting the surface that left craters. And why are there craters? There's basically no atmosphere to slow them down. How many craters do we have here on Earth that we know about? Say again? No, that's just a canyon, okay? We probably have a few that have been overgrown since prehistory. Very few things, meteorites hit the Earth. There was one that hit in Siberia not many years ago.
Tungus.
Second?
Tungus. That was called Tungus.
One that may have been, okay. What, about 5-6 years ago or something like that? Maybe a little longer? I don't remember. It was not long ago, one hit in Siberia. They thought that was an asteroid, not a meteorite, but whatever's falling from space, I call it a meteorite. And that probably left a crater you can still see, probably. On our farm in Georgia, they say if you look at a topographical map, you can kind of see a depression there that's a bit unnatural, and we have found chunks of iron around that, though I don't know exactly where it is, but we found that nobody else finds much of that around. So we may have one there, but it's so overgrown you can't pick anything out. But you see, Mercury has no, the reason we have a nice thick atmosphere. And when any piece of space stuff comes in, it generally burns up before it gets through our atmosphere. Okay? So that's why very few meteorites or other things hit the Earth's surface to leave a crater. Mercury, no atmosphere, lots of craters. So it's real close to the sun. Most of the stuff that's hitting is stuff that's left over from comets. We'll talk about it later. Left over from other things, and it's being drawn toward the sun. And guess what's right in the way? Mercury. Okay? So it's being pummeled, probably fairly constantly, by stuff. Okay? And that's because there's no atmosphere to slow it down. It is now the smallest planet. Back before Pluto was redefined as a dwarf planet, Pluto was smallest, now Mercury is. In fact, there's probably, I'm just going to guess, 3 or 4 moons of the bigger planets that are bigger than Mercury. Okay, that's how small a planet it is. Okay? Our moon is close to the same size as Mercury, just a little bit smaller. Okay? This is what I mean by Mercury being hard to see. Now remember, all planets have phases, just like the moon has phases. Okay? And when Mercury is at its brightest, it's on the other side of the sun, almost directly in line with the sun, so it's going down right with the sun. You're not going to see it because it's on the other side of the sun. But when it's out here and just beginning what you would call its gibbous waxing phase, as it's a little bit more than half a moon, half a planet showing, that's when it'll be most visible, but it's sort of far away. When it's closest to us, we only get a little sliver of it, a crescent Mercury. Okay, we'll talk about that in the next chapter. Okay, this is seen from Earth, so it's really hard to see. This could be the sun setting or the sun rising. As long as the sun's up there, you're not going to see it. Okay, but once it goes below the surface, you might catch, and this is a really big angle here. It's only going to be when the sun goes down, it drags it right behind it. This is way exaggerated, the orbit here, way exaggerated. Okay, it's only going to be for a number of minutes, either preceding the sun at sunrise or following the sun at sunset. Okay. Here is a picture of Mercury taken by some of our things, and look at all the craters on it. I mean, it is pockmarked. Okay. incredibly pockmarked because all the stuff being poured through the sun, that'll just sprinkle it. Okay? That's Mercury. Now, let's go back. Now, in the next chapter, we'll talk about, well, wait, maybe later in this chapter, we'll talk about the formation of the solar system. I think that'll be later in this chapter. Okay? And we'll see that when the sun was exploding and going through its various things, trying to set up its dynamical equilibrium, it probably blew the atmosphere completely off Mercury because it was going through some pretty unstable times, and that's why Mercury probably has no atmosphere. Smallest planet, so it has the least gravitational field, so it's not going to hold on to much. And that close to the sun. Now, which do you think is the hottest planet? Hey, y'all are good. How do you know that? Don't answer that question. Okay, she's right ahead. Okay, it was sort of a trick question. On average, it's Venus. Okay? Mercury, however, the side facing the sun, like this one right up here, because that's where the sun is, that is the hottest you can of any of the planets, right at that moment. But somewhere down here in Mercury's midnight, it is incredibly cold. Because what's another thing our atmosphere does for us? It blocks out ultraviolet rays, it blocks out the deadly cosmic rays, it provides us, one thing it does is provide us insulation. So it keeps us cooler when we should be hotter and keeps us warmer when we should be cooler. So it's sort of like a big blanket around the Earth. Mercury has none. So when it's exposed to the sun, the side toward it, it's burning hot, but down here it's frigidly cold. So its average temperature is actually less than that of Venus. Very good for reading ahead. Okay? But instantaneously, the side toward the sun is probably incredibly hot. Okay. Any questions about Mercury? By the way, it has no moons, no satellites around Mercury, just a pockmarked chunk of rock. What kind of planet do we call it? Hint, rock. A T word. Terrestrial is one of the 4 inner terrestrial planets. Okay? The next one is Venus. Okay? If this is Sun, this is Earth, 4/10, a little over, less than halfway out, is Mercury, 7/10, closer to us, about equidistant from Sun to Mercury, Mercury to Venus, and then less than that from us to Earth, Venus to Earth. Our, except for the Moon, our very closest neighbor in the solar system. Okay? 7/10 of an astronomical unit from the Sun. Now, when it's up, except for the Sun and the Moon, it's the brightest thing we see. In fact, it's the first star. So it's not a star, it's a planet that we see in the morning if it's up, or the last one we see at night as no, I said that wrong. The last one we see in the morning, the first one we see at night, it will be Venus. That's the morning or evening star. It's not really a star, it's a planet. Now, half the time we're not going to see it. The half the time we do, it'll be that really bright one we see, first one that shows up, and they call it the morning or the evening star. Okay? If you have a good set of binoculars, or even a telescope, you can look at Venus when it does come up, and you'll see it has phases just like we saw with Mercury, just like we'll see with the Moon in the next chapter. Okay? You'll see full Mercury, Venus sometimes, you'll see half crescent, whatever. Now, it and Uranus are really strange in this respect. The rotational movement is opposite to the orbital movement. If it's going around the sun in this direction, it's spinning in that direction, the opposite direction from its rotation. So if you're on Venus, which you don't want to be, but if you're on Venus, the sun would rise in the west and set in the east because it's turning backwards. But you wouldn't see that very frequently because its day is longer than its year. It takes a longer time to spin once, and spinning backwards too, remember, than it does to go all the way around the sun. It's really a slow spinner, going backwards, slow spinner, and going around. So if you look at the table, you get the exact dates. I think I gave them to you before. Rotational period is minus 243 days, where its orbital period is 6/10 that of Earth, okay? Which is Earth years, that would be, what, about 7 months? So this day is longer than its year, okay? Now, because it's our closest neighbor, except for the moon, our closest neighbor, we have visited it numerous times, okay? Not landed on it, though we probably have crashed onto it, but we haven't set up a station there by any means, okay? But it's been visited by numerous probes. Even things not destined to go to Venus, they'll go by Venus, and I don't know if the guy at the planetarium will tell us this or not, but one way they do to save on fuel. I'm trying to think. Did y'all ever play a game when you were young called Crack the Whip? No. Okay. There would be some long string, and everybody would be hanging on to it. And someone's leading and stuff, and then make sharp turns and stuff like this. That person on the end gets slung way out there because they're at the very end. It's called Cracking the Whip. Have any of you? Yes.
Wait, so like on the ground, it's like slingshot defines gravity?
What's that?
Is slingshotting by gravity?
Yeah. Okay. You're being slung by Venus's gravity. Is that what you're asking? Yes, you're absolutely right. Any of you water skiers? No? I'm not either, but if you get on the outside of that boat when it's making a turn, you're flying out there. If you get on the inside, you're going to sink because there's not enough to pull you around. So that's what we're doing when we go by Venus. We get swung around and it sends them out further away. You get into a very highly elliptical orbit, and you use Venus's gravity to pull you in and sling you out. So even when we're not going to visit Venus, we will still visit Venus by numerous probes. Now, its atmosphere, I think I pointed this out, mostly carbon dioxide. And the next planet out is, besides Earth, is Mars. And guess what Mars's atmosphere is? Mostly carbon dioxide. Now, Mars has a very thin atmosphere, okay? Venus is incredibly thick. What do we call CO2 in our atmosphere? What kind of gas? A greenhouse gas, because it traps heat from the sun. So, Venus, mostly a very dense atmosphere, mostly CO2, mostly a greenhouse gas. It has incredibly high temperatures and high pressures, and a very thick atmosphere which insulates and holds that heat in. So day or Venus night, it's going to be hot. Really, really hot. Okay? And because it's a really dense atmosphere, the pressure is quite high too. So you don't want to live there. If women are from... No, we won't go into that. Okay. We won't do that. No. Okay. It's, I would say, hostile. What's not CO2? There's a lot of sulfuric acid in the atmosphere too. Not a particularly pleasant place to be. Okay? The surface is mostly flat, but does vary. And I think what picture we're going to have here, maybe not immediately, this is some of the probes that have gone to Venus. Now, This is sort of old, starting in 61, 63, 64, 65, 67, 69, 70, 73, blah, blah, blah. 73, 80s, 83, 84, 89, they stopped around then, okay? Not that the probes have stopped, but they stopped recording them in this table, okay? The owner of these probes, if you'll notice, is mostly, anyone even recognize what that is? US is us, okay?
Yeah,
Literally.
the
USSR is
Russia.
Union of Soviet Socialist Republics, which we call Russia, but it was just one of the republics. That was the USSR, okay? Notice they went there more frequently than we did. We were in the space race, remember? They got a head start on us. They were going there, so we decided we'd go to Mars, okay? Since they were going there, we were going. It wasn't that we were sharing data, though we did. Yeah, we really did. But it's just that if one said the sky's blue, the other said it's green, you know. They just don't do opposite from each other. So yeah, that just shows how frequently various groups have gone to Venus. If they went there for Venus, then you'll see Venera 1, Venera, these are the Russian names. The others, Mariner, guess where that was going? Ultimately. Mars, not Venus. But we're going to zing around, and that was mostly us. Mariner, okay? We were just using it to send us. Now, we also did some others that we were doing other things too. I can't read that. I think it's Pioneer and various things like that. But, yeah. So, anyway, visited many times, many pictures taken, many ways of taking pictures, and here's a surface shot. They did drop something down into that thick atmosphere and lower it down there, and it got a topographic thing before it crashed and burned. How it got this far, I don't know. That appears to be a pretty big volcano there, okay? And this seems to be streams of lava, so that's a pretty active seismic, logically, you might say. Lots of activity going on there. But anything that was on the surface, it's not going to have any water flowing in a valley. That'd all be steam if it had any water, okay? This is going to be molten metals or something else that would be flowing along there. Not an hospitable place. There probably is some water there and water vapor, and if it is, when water mixes with CO2, you get carbonic acid. When it mixes with SO2, which I think there's plenty of, you get sulfuric acid. So not a very pleasant place to be. Okay. One of the shows at the planetarium, if we get to go, focuses a fair amount on Venus, and it's pretty incredible what they've found out from these various probes. All right, we're going to skip good old Earth and go on to Mars. Now, Earth is one astronomical unit from the Sun. So we have the Sun, 4/10, Mercury, 7/10, Venus. Earth is at one astronomical unit. Mars, 1.5. So if this was Earth to Sun to Earth, then half that distance beyond, that's where Mars is. So you see there's 4/10 of astronomical unit, 4/10 of astronomical unit, 3/10, 5/10. Mars is further from us than any of the other two interior planets are from each other. Okay? Adjacent ones. 1.5 astronomical units. It's got some geologically active regions. Okay? Now they say active, but then say inactive volcanoes. They have been active in the past. Maybe not so much anymore, but they have. Now, the interesting thing is they have canyons. Who mentioned Grand Canyon? What formed Grand Canyon? Not a meteor. Water. Say again? Water. is erosion from water, flowing water. Now, what could form a canyon on Mars? Only thing I can think of is liquid water. I can't think of any other liquids that would flow and make that. Do we detect any water there now? Not really, except under the ice or under the polar regions, they have detected there's ice under there. Underneath the surface dirt or whatever is there, they have determined there is some ice on the poles. So obviously there must have been water at some time. Okay? There are terraces, terrace plateaus near the poles, which would almost indicate that there was some erosion of those poles. That's what makes the terraces, we think. We don't know. Now, many flat regions are pitted with craters. Why do you reckon that would be the case? A very thin atmosphere. So the atmosphere doesn't block many of the incoming particles coming from space, so therefore it's very pitted with craters. Very thin atmosphere, mostly CO2. Now, why would the planet next inside of us have a CO2 atmosphere and the one outside of us have a CO2 atmosphere, but we have just trace amounts of CO2, probably less than 1 or 1.5%, okay? Trees. Our little green plants are constantly taking that carbon dioxide out of the air and putting oxygen back in. Oxygen is very, very reactive, and if you didn't have those little green plants, I think we'd have a CO2 atmosphere as well. Still have more nitrogen than CO2. Why we have nitrogen the others don't, I don't know. Okay, we're just blessed. I don't know, but we don't. The others don't seem to have that much nitrogen.
Okay. That's what the G7 countries are helped putting out the fire in there.
Okay. Yeah, you nailed something that really gripes me is the tropical rainforest, the biggest chunk of which is in the Amazon area in Brazil and neighboring countries. That is the biggest source of air purification we have on the planet. It's taking tons and tons and tons of carbon dioxide and building plant material. And it's being a carbon sink, you might say, trapping it. And when you go in there and just burn and burn and burn, you make it a carbon dioxide source, okay? Because now that all that carbon is released into the planet, who knows what kind of damages that's doing to the entire global system. So yeah, G7, I think Macron was very wise to make that a top priority. And evidently it got someone's attention because they seem to be doing some stuff. Okay, strong evidence for liquid water in the past. Very little evidence that there's liquid water there currently. They have detected some ice under the surface near the poles, but liquid water. Now, again, very thin atmosphere. If that water vapor was in the atmosphere, it seems like it loses its atmosphere pretty easily. It's a thin atmosphere. It could be that next soul. Well, that's too far away, but you would think, what's happened to it? Has Jupiter stolen some of it? Well, that's pretty far away to do that. But Jupiter is a thief, so we'll see that later. Numerous space probes have gone there too. Now, this is not a feature. That's where something landed on Mars, on the surface. But what's Mars typically called? What's its nickname? The colored planet. What color? The red planet. It's mostly highly oxidized iron. And what's another word for oxidized iron?
Rust.
Rust, exactly. And rust quite often occurs where water is. Okay, so that's another piece of whatever. Okay. This is another picture. Now this, they point it out as if it's really significant. To me, this is one of the old stream beds, it looks like. And they say that the angular, I can't make up that word, uniformity or something like that indicates that water probably flowed in that direction. I can't make that out from here, but they say by looking at the shadows and the angles and stuff, it looks like that could have been a riverbed or something, a stream bed or something like that. I can't justify it, but I'll take their word for it. Okay? Whoa! We had the table of visits to Venus, and that, by the way, is on page 383 in your text, along with some nicer shots of Mercury on 382. But that list of, by the way, let's go back to this a moment. Okay, I said that this was the older figure. This one ended, it looks like in 89, which is right about here. Galileo, that's the one that was sent by the U.S. There have been two more added here, 2006 and 2007. A new kid on the block here, ESA. Anyone know what that stands for? European Space Agency. Okay, that was Venus Express. Okay, an orbital spacecraft. Messenger was just going by, so it's flyby photos they took, 2007 from the U.S. Okay. If you see RSA, that replaced USSR because that's now the Russian Space Agency. They're no longer USSR, but they're Russian, but I don't see one on here. All right. Mars. Here is a similar table for Mars. I thought they were going to show it here, but they didn't. And starting in 64, 70s, 80s, and you'll notice here, even though USSR is pretty frequent there, US, more of US there, and here's the ESA, European Space Agency, and here is another new kid on the block. India sent out an orbiter to Mars. That's the most recent that's listed here, 2014. Okay. Now, this is kind of like that Space Objects in Perspective, the slide that I told you about, I put out there, the file I put there. This is size comparison of the four rocky planets. What's another word for rocky? Terrestrial planets. There is Mercury. There is Venus. There is Earth, slightly bigger than Venus, but not much, very close to the same size. Here's our moon compared to Mercury. Not far off. Our moon's a little smaller than Mercury, but it's close. Here's Mars. Now, they're not this close together, folks. Don't even imagine that. Never are they lined up like this. This is just when they're put on the same scale. There is one of Mercury's two moons, probably their larger moon. Look at the difference, folks. Our moon is huge compared to our size, compared to what any other moon is to any of its planets. That's typical. A moon to Mars, it's piddly. Our moon to us, we'll talk about this in the next chapter. Okay? So anyway, that's Mars. The red planet. Those are the four inner planets called terrestrial planets because they're rocky in nature. Okay. There was Mars. All right. What did we have to jump over? The asteroid belt, exactly. So here was the sun, okay? Here was Mercury, 4/10 of the distance from Earth to Sun, a little less than half. Here was Mars, Venus, another 4/10 closer to us, 3/10 from us. We are, Earth, right here. And then half this distance again, there's Mars here. Then there's the asteroid belt. And 5 times the distance from Sun to Earth, 5 times that, is where you finally get to Jupiter. way out there, okay? In between that is the asteroid belt, okay? About 5 astronomical units from the sun. 5 times as far from us to sun as sun to Jupiter. Whoa. The most massive planet by far, okay? 318 Earths to match one Jupiter in mass. Now in size, it's even worse, because Jupiter is a gas giant, okay? But in mass, 318 times Earth's masses. It's made up mostly of hydrogen and helium. Now, in its core, somewhere out there, way in the core, is an iron silicate core. Our core is also iron. Ours is more iron nickel. We have silicates near the surface, but iron near the core. They have an iron silicate core. Jupiter does. I say they. It's so big it seems like it's more than one. So here's a pictorial of that. Okay? The iron silicate core, you could fit 10 to 15 Earths in just the core of Jupiter. 10 to 15 Earths just in its core. Okay? Then you have what they call a strange name, liquid metallic hydrogen. Okay? Now that's weird. Okay? Liquid, metallic, which sounds like a contradiction in terms, liquid metal jumper, but liquid metallic hydrogen. What I think they mean by that is, okay, back off a moment. Hydrogen is the lightest gas, right? First thing on the periodic table, the lightest gas there is, and it is a gas, for sure. What would you have to do to make it liquid? Cool it, cool it, cool it, cool it, cool it. In fact, get down to, remember we talked about absolute zero, didn't we talk about that? I think you're within 4 degrees of absolute zero before you get into liquid hydrogen. Now that means that this is awfully cold. Or, what's the other thing you could do to make it a liquid? Pushing those molecules closer and closer together.
A strong gravitation.
Okay, pressure. A very strong gravitational force on it. Now, that tends to make it hot, okay? So you have some weird combination of this cold. I don't think it's that cold, but it must be pressure, okay, that forces it into liquid metallic hydrogen in the outside the core. Look at that. 35,000 kilometer thickness of that liquid metallic hydrogen portion. 35,000 kilometers. For comparison, the equatorial diameter of the Earth is diameter. This is across the Earth, less than 13,000. Okay, so just about 3 Earth's diameters could be fit inside that band there. Okay, 10 to 15 Earth masses are in here. At least 3 Earth's diameters are in this part, and then the next part is there it is. Liquid hydrogen, that's about 20,000 kilometers. More than 1 Earth can fit in that. Close to 2, okay? Not quite 2. Liquid hydrogen, now that I can believe to be very cold. You don't have as much gravitational force here, but that's quite cold because this is way far from the sun. So I can believe that's due to coldness. This part in here, because this is an iron silicate core, that's under a lot of pressure. So I think this is more pressure. And I'm sure that's not a direct, clear boundary like this. It probably integrates slowly. So anyway, it's pretty amazing. And then it does have a thin atmosphere, and that atmosphere is hydrogen, helium, and ammonia. And these are clouds, and that's about 500 kilometers thick. Okay, just as a reference. Well, it doesn't give the thickness of our atmosphere, does it? Just the compounds. So it's a pretty thick atmosphere. Okay, mostly hydrogen, helium, and ammonia. Now, what I find odd about ammonia, where do we find ammonia? Where is it fairly common? Second, what's it made up of? Anyone know what ammonia is made up of? Hydrogen and nitrogen. So there's the nitrogen. Theirs is not N2 like in our atmosphere, but they have it in their atmosphere as ammonia. And this is a little on the gross side. Back in the pioneer days, they didn't have soaps to wash clothes. You know what they used? Second? You got it. And urine contains a lot of ammonia. And that's why. It's mostly a compound that I think of coming from life. There's no life on Jupiter, okay? As far as I know, never has been, never will be, okay? Not going to happen there. And yet they have clouds of ammonia. So things that I always thought, and I thought CO2 came from living organism. Not necessarily, okay? We've just seen nothing lives on Venus, yet it has a CO2 atmosphere. So a lot of things I find surprising here because I would never have expected ammonia there. We'll leave it at that. Okay, here is a picture, an actual picture of Jupiter. And I don't believe there's been any color enhancement here. This is what it looks like. What you see here are bands in that very thick atmosphere, 500 kilometer thick atmosphere. These bands are going, because Jupiter is spinning, so the atmosphere is in bands. The different colors of the bands represent different temperature ranges and possibly different components. This thing right here is called the Great Red Spot. Okay? It is so large that even, I think, Galileo, when he first improved the telescope that he could see Jupiter well, I think he identified the Great Red Spot. It is a storm that has been raging for hundreds of years. Raging for hundreds of years. Now, last I've heard, it seems to be shrinking. So maybe it's diminishing, and maybe one day there won't be a Great Red Spot, but it is an incredibly massive storm that you can see disturbing the atmosphere there. And it's been happening constantly for literally hundreds of years. Okay? The other specks and spots, I think these are cold areas, and some of them are hotter areas. I can't remember which way it is, but there are other storms that are going on there. But that's the Great Red Spot, indicating an enormous storm that has constantly been raging. Okay. There's Jupiter. Now, I'm skipping over many of the examples in the text. It's not that they're not important, it's just that the math involved with them requires knowledge from the first half of the book that, since we haven't done the first half of the book, it's sort of tough to make you do. But I would definitely read through the examples. You'll find very interesting facts and features there. Okay? Now, let me also mention this. there's periodically these little blurbs called science sketches. They're pretty small. If you're interested in doing it, by all means do those. There's one at the bottom of page 385. But there's also things like case studies. The question is worth the cost, and it mentions some of the cost of, say, space probes and things like this, things being sent out to Mercury and Venus and things like this, and you say, isn't that costing a lot of money, and what are we getting for it? This little blurb at the top of page 386 begins to at least maybe answer some of those questions for you. Okay? Now, okay, now I may have said, yeah, no, I think I said it right. The darker features of Jupiter are the hotter regions, warmer regions. The lighter features are the cooler regions. Okay? And the great red spot, it's red in the middle, but surrounding it are some of the coldest regions, they say, on the planet. Okay. Though it looks like to me those are fairly dark. That's why they call it the great red spot. So some of this I find almost contradictory. So let me mention this also about Jupiter. I wanted to make sure it was in your text. The thing I was saying about it's getting smaller, I don't see it in here. I think I heard that at the planetarium or read it or somewhere. So I don't want you to be responsible for something like that. But here, I think we have a slide of it coming up. Okay, let's go back here. Jupiter has a dynamic atmosphere. That means it's moving, it's changing, it's storming. Okay, mostly hydrogen, helium, ammonia. Also methane. Anyone know what methane is? CH4, exactly. It's a very volatile gas. It's what some of the high performance race cars, they burn methane rather than fuel, as their fuel, not gasoline or something. Water, there is identifiable water on Jupiter. There seems to be all through the universe. So it's not surprising that there will be some on Mars, and you would be surprised to find any on Mercury because it's so hot it's evaporated away. Okay, the great red spot, we've talked about it, and it has a large system of varying satellites. Now, what do we mean by that? What's another name for satellites? Moons, exactly. Your text says tens of moons, and it seems like to me I've read somewhere, and I can't find it. It's not in here that I don't think. At one time, they had identified at least 52 moons, and I think since then maybe have found more. It's surrounded. I mean, but it's a huge planet. It's a huge, huge planet. Large system of varying satellites. Now, anyone want to make a guess of maybe why it has so many moons? What's it? Yes.
Because of its size, it attracts gravitational.
Second.
Because of its size, it attracts gravity.
Okay, it has a huge gravitational field, so huge, in fact. Okay, I'll get to your moon thing, but so huge that between now the sun, remember, is 700 times bigger than everything else put together. Okay, so the sun is enormous. Okay, but Jupiter is big enough that I can't remember if it's Fourier analysis or some sort of analysis. It contributes. It doesn't exactly rival the sun, but the things that are closer to it, it has enormous gravitational pull. Okay, so yeah, its big gravitational pull, it's always pulling stuff in. Okay, now what's just inside Jupiter? I've mentioned it a few times. between Mars and Jupiter? Say again?
The asteroid belt?
Can't hear you.
The asteroid belt.
Yes, the asteroid belt, exactly. And you can't convince me Jupiter didn't rob some of those asteroids. Some of them maybe got a little lagging or drifting and stuff, but Jupiter pulled it right in. Now that's my guess. That's just my guess. But anything else going by, there's a good chance Jupiter is hung on to it. So, large system of varying satellites, meaning moons. Okay? All our book says is has tens of moons. I think that's 5 or 6 tens of moons, 50 or 60. Okay? Some of the smaller ones are still yet to be discovered. Now, there is the great red spot in the upper part of that picture. Below it is one of the coldest regions in Jupiter, and that's the little accompanying white spot. Okay, sort of like a pimple near the red spot. I don't know. I didn't say that, did I? Okay, never mind. Okay, you didn't type that, did you? No. Oh no. Okay. Now, these. Any idea what these are? These are the 4 largest of Jupiter's moons. Now, in your text, it's a slightly different picture. I think a little bit nicer picture. And let me see if I can hit these in the right order. The next to the smallest, upper left, is Io. I-O. Okay. I-O. I pronounce it Io. I don't know. It may be I-O. I don't know how you pronounce it. Okay. And then Europa, which is the smallest of the 4.
Is that like EU?
Huh?
Is that EU?
E-U-R-O-P-A. Europa. Sort of like Europe. It starts like that, but it's A at the end. Okay. Then Ganymede, which I think is the largest, and that's G-A-N-Y-M-E-D-E. And then Callisto, C-A-L-L-I-S-T-O. Now, Io and Europa are about the size of the Earth's moon. These 2 smallest ones, that's about the size of our moon. Now, wait a minute. These are the 3rd and 4th largest moons on Jupiter, around Jupiter, and yet the Earth, which is so many times smaller than Jupiter, it's just not even. It's just amazingly, it has moon that rivals the size of those 2. Our moon is way out of proportion to our Earth. Way out, okay? Whereas Ganymede and Callisto, the 2 bigger ones, are slightly larger than Mercury. And Chris decided to grace us with his presence today. Good deal. Okay. How are we doing on time? Whoa. Ooh. All right. So I think the only student we're missing is Ken. Is that right? Wow. Good attendance, people. Great attendance. Okay. Now, I think there's one more pretty significant shot here. Nope, it's not. It's going to come up in the next chapter. In your book, it's in this chapter. This slide set came from an earlier edition, okay? So, and that's a picture of a former comet that made the mistake of getting a little too close to Jupiter. And it got sucked in and left a trail of bright spots where it entered the atmosphere and was destroyed. Can anyone guess what astronomer discovered that? I don't know the guy's name, but he was an amateur. He was someone who just liked looking at the... Say again? No, not Galileo, an amateur. Now, let's go back to Galileo. You know what these moons are called? The Galileo moons. And that's named after, not the Sea of Galilee, but Galileo, who was the first to see these when he made his improved telescope. I don't remember who had first invented the telescope, but he read about it, studied about it and came up with a vast improvement, saw many times bigger things. He looked at Jupiter and found 4 moons around Jupiter. He saw, I think he saw the great red spot. He saw it was moving, and that is pretty much what convinced him that Copernicus was right. He said, if the moon, our moon spins, and he could tell that did, well, he couldn't really. Okay. But if Jupiter spins, and he could tell that by the movement of the great red spot, and he saw these moons around it and saw they were spinning, he said, wouldn't it make sense? And also, I mean, even the sun has these sunspots, and you see them moving day to day. He said, wouldn't it make sense that we would be spinning? And if we're spinning, then that accounts for the movement of the stars around us. It's not they're moving around the Earth that everybody thought. Makes sense. They look like they're moving. They're not. If these other things are spinning, we must be spinning, and therefore the stars, which are fixed pretty much, look like they're spinning, moving. So that's what convinced them Copernicus was probably right. And therefore he got into deep trouble. Okay? Copernicus, believe it or not, if I'm not mistaken, was a monk. And of course the Catholic Church was the big resistor to any talk of anything other than Earth being the center of the universe. But Copernicus was very bright too. He had 2 things in his advantage. Number 1, he lived way out in Poland, far from the Vatican. Okay? The other thing, he was old, and he refused to let any of his writings get published until after he died. Okay? So it was his assistants who then published, and that's where the Copernican theory came from. And they couldn't excommunicate him. He was already dead, so couldn't kick him out of the church. But then when other scientists started believing that, as in Galileo, Galileo got put under an inquisition, probably came pretty close to losing his life, but because he was such a famous scientist, they just put him under house arrest. And they worked on, and I think the condition that he continued living was he had to recant everything he had said. So he formally did that, and at the same time wrote down, and I didn't mean it, and other things to be published after his death, and he said, no, I really do truly believe Copernicus' theory. But that's another issue. All good things you could look into writing about. But anyway, this, let me see if I can remember its name here. Strange name. Levy, something another. Schumacher-Levy 9 comet just came a little too close to Jupiter and got sucked right in. That very powerful gravitational field. That we'll see in the next chapter slides. So let's move on out to Saturn. So remember, Sun here, Mercury there, Venus there, Earth there, then 1.5 times Earth is Mars here, then you have the asteroid belt, and 5 times the distance from Sun to Earth, Sun to Earth, is where you find Jupiter. 5 times as far, I'm way too close. And then Saturn is almost double that. 5 times to Jupiter, 9.5 times to Saturn. Remember that picture that showed these things fairly close? They're not. These later planets get farther and further and further away. And Saturn has that beautiful ring of particles. That's how we tell Saturn. But guess what? All those gas giants have rings. Jupiter, Uranus, and Neptune's just pitiful little rings. You don't even notice. Saturn, though, oh my goodness. Incredibly beautiful rings. We'll see a picture of it coming up. Here is the most amazing thing about Saturn to me. The rings of particles, that's probably most. Next to that is density. 0.7. That's less than the density of water. If you had a big enough bowl, Saturn would float. Okay? Of course, we don't have big enough bowls. Okay? The surface is very similar to Jupiter's. Okay? And it has 30 satellites. So I'm pretty sure Jupiter's is in the 50s or 60s, okay? And Saturn's largest moon is called Titan, which is a pretty good name for it. It's the only moon with a substantial atmosphere. Think about this. Mercury, the planet, doesn't even have an atmosphere, and yet Titan, I think the largest moon of Saturn, and I believe it may be larger than Ganymede and Callisto. I'm not sure, but I believe I've read that somewhere. And it's quite a bit, I think, larger than Mercury, or somewhat larger than Mercury as well. But that's Saturn. Okay, there is a picture actually taken by, let me see if I can remember. Huygens was part of the name. Cassini-Huygens, I think it was a European Space Agency spacecraft that made its way to Saturn. It took some of these beautiful, beautiful pictures of the rings. Okay, I think that one is from Cassini-Huygens, but I'm not absolutely certain of that. Okay. Okay. Then it moves on, our book moves on. Your text does a little bit more, and this is worth a look. We don't have it in the slide set, but figure 1512 on page 390. Saturn's rings are made of an enormous complex structure, and they have names for them, A, B, C, and D rings, very creative in those names, and then has some outer rings from that. From edge to edge, the ring system would not even fit in the distance between our Earth and Moon. Okay? So it's a really big ring system. Okay? I'm trying to find, oh yeah. Titan is a moon that's way out there. Okay? Titan's orbit is about 1 million kilometers. That's 621,000 miles from Saturn. 621,000 miles from Saturn. The distance from Earth to Sun, 93 million miles. So this is about 100th of that distance. A little more than 100th of the distance. It's incredible. Okay? So pay attention to your book. It has a little more detail than what the slideshow here shows. Okay? Because we're still learning stuff all the time. Because if you think about it, instruments that were sent up years ago, if they're sending back stuff, it takes quite a long time for us to get it back, and then to analyze it, it takes even longer. Okay. So let's go to the last two. Now, they don't give these separate things. They just say Uranus and Neptune. Now, look at how far these are. If you remember, Sun to Mercury, 4/10 of the astronomical unit. 7/10 to Venus, 1 to Earth, 1.5 to Mars, then the asteroid belt is there, 5 astronomical units to Jupiter, almost twice that, 9.5 to Saturn, now to Uranus, 19. So doubled again. You're doubling the distance every planet you go. So Uranus here, Saturn is halfway between the Sun and that. There's nothing between those two. And then now Neptune's not quite as far. It's only 30, so it's not quite double, but it's still way, 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 way out there. If this was Sun and this was Earth, 30 times this. I don't know how far out into the woods that would go, but it's somewhere way out there would be Neptune. These are the outermost giant planets, very similar to one another, very similar in internal structures, similar to Jupiter and Saturn, but on much smaller scales. Okay? There wasn't too much known about them. This is a picture, I'm pretty sure, of, I think that's Uranus. I'm not absolutely certain. No. In your text, they don't have this one in the book. They have a picture of of Uranus, and it's figure 1513 on page 391. I wish they had it here, but it probably wasn't in existence when our book was published. And it shows, and it's taken from the Hubble Space Telescope. Notice how the atmospheric weather bands in the ring system tipped on the side compared to Saturn. So that's why we say it's turning backwards, because it's almost perpendicular to what all the others are, but it's tilted slightly, but this is the way the rotation is not, it's rather strange, okay? Next to Venus, the strangest in its rotation. Okay, this I think may be Neptune then, okay? And this again observed from Hubble Space Telescope, nearly the same size as Uranus, but more than twice as far away from the sun. Now, not by this, okay? Not twice as far as, oh yeah, it says nearly. No, it says more than. That's not twice, okay? So I don't know. Either this caption is wrong here, or the, let me just see. Yeah. According to the numbers, that's not twice as far. It's a long way further, but not twice as far. Okay? The most recent mission that we sent out that way took some really incredible pictures of these planets. We know a little bit more now than we did. They haven't made their way down to textbooks yet. Okay. All right. That's all they give on this. Hopefully, if we go to the planetarium, we might learn a little bit more about these outer two planets. Okay. Started with the terrestrials. Those are rocky planets, the four inner. Asteroid belt, which is mostly rocky. Then we got to the gas giants, gaseous. No identifiable surface of those, just thick, okay? And now we go back to smaller bodies of the solar system. The main three we're going to focus on, classifications, are comets, asteroids, and meteorites. Now, I wish they hadn't said meteorites and said meteoroids here. We'll get about the difference later, but I know what they're saying. These are leftover pieces from the solar and planetary formation. When our sun was forming and exploding and going back and forth and stuff, it was spewing stuff out there that didn't all come back, and that some of that made the planets, and some of it made these other smaller bodies. Now, this is the figure, the caption, the wording that I said beware about. Is this one right here. The mass of the smaller bodies may be 2/3 of the total solar system mass. What does that contradict? Remember that first thing I pointed out to you on one of the very earliest slides. It wasn't on the slide, but I said beware of that. First page of the text, the actual text of this chapter. The sun is 700 times more massive than everything else in the solar system put together. So this is 2/3 of the total solar system mass excluded from the sun. This counts Jupiter and Saturn and Uranus and Neptune and all the other planets and everything else. The total mass of these smaller bodies is 2/3 of the total solar system mass, not counting the sun. The sun is 700 times more than all the rest of it put together. So that's the way they word this. Can't be true if the other is true. Okay. Now, these things, these smaller bodies, bombard larger objects. For instance, this is where it is. Okay, not under Jupiter, but here. This is it. This is Jupiter. Okay, and it got poor old comet Schumacher-Levy 9, or I think it's Schumacher-Levy 9. Its fragments strike Jupiter's surface. It got a little too close in July of 1994, and this was first detected by an amateur astronomer who was just out there admiring with his little telescope or whatever he happened to have, looking at Jupiter, because it's just an enormous thing to look at, and notice, what in the world are these little bright lines, these little dots along a line there. So the next morning he called whoever the agency was to call and said, what were those things? I saw them. What are they? And they said, what things? And they sort of got a description. So the next night they looked and they said, whoa, what is this? And then they went backtracking and plotting and thought, oh, Schumacher-Levy 9 was supposed to be passing pretty close to Jupiter. We can't find it anymore. Guess where it is? Sucked into Jupiter's atmosphere and destroyed. Okay? July of 1994. Were any of you born then? Yeah, most of you were born. No? Oh, shucks. Okay. Yeah. Okay. I was 41 years old then. Sorry. Yeah. Okay. Makes me feel ancient. Okay. 43 years old. Okay. Now, let's start with the comets. Where do comets come from? Where do they live? Where do they... There's two major locations for comets. One is called the Oort cloud. Now, boy, what a weird name is that, okay? The Oort cloud. This is the origin of the long period comets, those that are greater than 200 years in their traveling around the sun. Now, comets have incredibly elliptical orbits, meaning sometimes they come fairly close to the sun, but most of the time they're way, way, way far from the sun. And they take about 200 years to make one orbit, greater than 200 years, if they come from the Oort cloud. Okay, remember, Neptune was out there about 30 astronomical units. So these are from the outer part of our known solar system, Neptune, to up to a light year away. Still revolving around the sun, but very, very slowly. Okay? One light year away. The Oort cloud. Just a huge cloud of bodies that are out there. Now, I've heard this pronounced several ways, and I don't know the correct pronunciation. I think it's Kuiper, but I've heard it pronounced Kuiper and all sorts of things. I've even heard someone put in a T in there and call it the Kuiper belt. Not correct. Okay, it's either Kuiper or Kuiper. It's a foreign name. These are the short period comets, less than 200 years orbit. This is a sort of a spherical cloud, the Oort cloud. The Kuiper belt is more of a disc-shaped region, and this varies from 30 to 100 astronomical units. So there is some overlap between the Oort cloud and the Kuiper belt, but most of the Oort cloud is beyond 100 astronomical units, whereas up to a light year away, whereas this disc-shaped region is from Neptune 3 times as far, okay, 100 astronomical units. The gravitational nudges deflect the object toward the sun. They could be just hanging around there for long periods of time, but then something happens, something else comes close, pulls it a little bit, and now it starts going toward the sun, okay? This is a pretty good rendition of the distances we're talking about, okay? This little bit in here that you can't make out at all, That's the sun at the center. Now, it's probably much larger than that, but if you made it its regular size, it would bleed out everything else. But the sun's at the center. There is the orbit of Uranus, I think it is, the orbit of Neptune, and here's the orbit of Pluto, a dwarf planet. See how far out of tilt it is? That's one thing that makes it a dwarf planet, not a regular planet. Angle, very elliptical orbit. All of this that you see here fits in that little space right there. You know, just that far. Okay. Outside that, okay, that's where the Kuiper belt is. That's the disc-shaped object here, and the Oort cloud on out beyond that. No wonder 2/3 of the mass of the universe, of the solar system, except for the sun, 2/3 of it is out there. Okay, let's look at this. All that we know, Jupiter is somewhere in here. Okay, the sun is somewhere in there and stuff. These are enormous distances away. Think of how many of these bodies are out there. And you add all the masses, even though each mass is really small, add them all up. And yeah, 2/3 of the total mass of the solar system, excluding the sun's mass, is occupied by these other bodies. Okay? And yeah, I can believe that something out here does get nudged toward the sun, starts the trip, takes over 200 years to make that trip. Yeah. Now, it may not come super close to the sun. It may come relatively close to the sun. I mean, it's an amazing system, okay? Enormous in size. And we're just one little speck in the Milky Way. I mean, if you think about that. And the Milky Way is just one little speck in the world of galaxies. You know, there's billions and billions of galaxies. Unbelievable, the sizes and the dimensions and the masses that we're talking about. All right. That was the origin of the comets. Now let's talk about what their structure's like. Okay? They're small, relatively small, solid mostly, okay? And one of the models is a dirty snowball, okay? That's frozen water, believe it or not. There's water out there just flying around the solar system, okay? Frozen water, frozen carbon dioxide. Anyone know what we call frozen carbon dioxide? Dry ice, exactly. Dry ice, okay? Rock concerts and stuff like that. Yeah, well, y'all know about that, okay. Ammonia, there's ammonia and methane again. I thought came from living stuff, not necessarily. And that's the frozen part. The dirty part is the dust and rocky bits that are frozen in the snowball. Frozen water, carbon dioxide, ammonia, and methane. Now, two parts of these. You have the head, which is mostly the frozen part. It's a solid nucleus and a coma of gases around that nucleus. These are the things that have begun to melt from that snowball, and those are the coma of gases around that. There are two types of tails. One type is ionized gases. Now, does anyone know what an ion is as opposed to an atom? An ion is an atom with a charge. An atom is neutral in charge. Same number of electrons as you have protons. Okay? An ion has either a deficit of electrons or a surplus of electrons. The number of protons stays the same, but the electrons vary. And these would be ionized gases. They could give off their own light. Are there any ionized gases in the room right here? Yes, the fluorescent tubes. Now, an incandescent light bulb is just heating up a filament and that gives off light. There's no ions involved with that, okay? But these fluorescent tubes, there's usually what they call a ballast in there, which is a very strong capacitor. And that builds up quite a charge difference, and that charge difference between the ends that ionizes the gases. They go flying back and forth, and there's a phosphorescent material, that white powder inside the tube. When those ions go flying by, it excites the gas. The electrons jump up a level, and when the ion passes, they fall back down, giving off the photon of light. That's how fluorescence works. So yeah, ionized gases, they can be giving off their own light. The other type of tail is dust. That's just reflecting light. As it gets closer to the sun, then you'll see that tail. Now, here's a picture of an actual comet. Okay, where is the sun in this picture? I mean, you don't see it in the picture, but where would it be relative to the picture? Yes, over here somewhere. Somewhere here, the comet head always points toward the sun, the tail pointing away from the sun. Which way is this comet moving? Impossible to tell. You might think it's going toward the sun. Not necessarily. It could be going away from the sun, or it could be going in this direction, but the head is always toward the sun. So wherever it's moving, this is how it looks. Now, can I tell whether this is ionized gases or dust? No, I can't. It's just could be dust reflecting the light of the sun, or it could be ionized gases, which could be putting off their own light. That's what a comet looks like. The head is what's made of the sturdy snowball, and then these are the tail is the gases out there, or dust. All right. Yes. Oh, yes. Why don't we take a break? We've been going at it quite a while. I thought if I had finished the chapter, we'd already be doing the lab by now, but nowhere close to that. So let's take a break. We'll pause it here. Let's see, we'll start the next one. Let's see, there is a little bit more I think we need to say about... No, we'll start with asteroids. That'll be next. All right, let's pause. Okay, of the smaller bodies in the solar system, of course, we have the sun, which dominates everything. Then we have the planets, 4 inner terrestrial planets, 4 outer gas giant planets. In between that, those 4 inner and outer are your asteroid belts, okay? And these are where the asteroids live. Out beyond the outermost planets, that's where your comets live, okay? And then we'll talk about the other one a little bit later. So here's the second group of the smaller bodies, the asteroids, located in a belt between Mars and Jupiter. Now, sizes up to 1,000 kilometers. Now, they don't say what that is. I think that's diameter, okay? Approximately, anyway. Varied composition, okay? The innermost belt are mostly stony, which is not too surprising because what are the inner planets? Terrestrial, rocky planets. So not too surprising, the inner asteroid belt basically are stony. The outer belts are dark with carbon. Now that's not very descriptive in my mind, the dark with carbon, but that indicates probably a little bit lighter material. And if you think about what does a centrifuge do as it spins, the heavier material comes in, the outer material gets, well, or whatever. So it's sort of that type of activity. Others mixed in there are iron and nickel. And where did I mention iron and nickel are located mostly on the Earth? The core, exactly. So this is just stuff that's left over from the formation of our solar system. Okay? Now, we think it's formed with the original solar nebula. So that nebula came together. What was a nebula, by the way? Nebula? A mass of gases, right? It's a huge mass of gases. It formed from that, from the original solar nebula, probably when the sun was kind of exploding and going back and forth, doing its thing. Okay? Now, there's a lot of evidence and people imagining that probably that should have been a ninth planet, okay, in between number 4 and number 5. But it was prevented from clumping and becoming a planet because of Jupiter nearby strong gravitational effect that just kept it from forming when the others formed. Blame it all on Jupiter. It's a big bully anyway, okay? Now, here's approximately the distances. Remember, sun's here, pretty hot. The Earth would be about here. 1.5 times from Earth is Mars. And then Jupiter's out here 5 times from Earth. The asteroid belt sits in between here, which is right about where another planet would be. Okay? It seems to be that would fit. The inner edge of sort of that belt is about 4/10 of the distance to Jupiter. The outer is about 6/10, so right in the middle, about halfway to Jupiter, from Sun to Jupiter. And guess what? Jupiter is about halfway from the Sun to Saturn, and that's right halfway. Yeah. So it fits. That seems like where that ninth planet should have been. Mean old Jupiter kept it from happening. Okay. Now, that's all they say about asteroids. Okay? On the slides. There is a blurb on there's a figure 1518 on page 395, close-up photo of an asteroid. Okay? The spacecraft Dawn obtained the image of Vesta, which is the name of this asteroid, on July 24, 2011, from a distance of about 5,200 kilometers or 3,200 miles away. The 3 vertically aligned craters have often been called, oh, you can't see it on the thing, the snowman. Okay? They just look like the big middle and top head of a snowman. Then on page 395, mistakes and misunderstanding, there's the statement here about asteroid belts. The astronomers have cataloged hundreds of thousands of asteroids, and asteroid means Greek for starlight, by the way. And the myth is that it's densely packed with chunks of rock. That's a myth. These things are way far apart. They don't bump into each other regularly or anything else. That's not, you would like to think they're floating around there as a big mass. They're not. Nothing in space is really close together. It's very rare that something gets close enough like Schumacher-Levy did to Jupiter to get sucked in. But it can happen. Okay. So that's sort of finishes up asteroids. Meteors, meteorites, but there's actually something before that, a meteoroid. Now, what is a meteoroid? It's the chunk of something out there in the solar system. Mostly remnants of comets or asteroids that got sucked in toward the sun. Comets are always going around the sun, but remember they're masses of solid material, and when they get too close to the sun, they're, remember, dirty snowballs held by ice, you know, and when that melts, chunks of rock are released. And the comets, anytime they come around, unless they pick up more moisture when they go back out, they're going to get smaller and smaller. So the chunks of rock that are left over, these are your meteoroids. They're just chunks of rock hanging around in space somewhere in our solar system. Now, what makes it a meteoroid become a meteor is when it encounters the Earth's atmosphere. It's not a meteor unless it encounters the Earth's atmosphere and then starts being sucked into the Earth's atmosphere, and then that's when we see it. And we pass these meteor showers, they call them. It's when we pass through a place where the comet's tail has been. It may have been years, tens, hundreds of years ago, the comet passed through there, leaving the debris, and then we passed through the tail, because we're moving. We moved through that. And guess what? Okay, you want to be sun again? You're really right. Okay. We go around the sun like this. If a comet came in over here hundreds of years ago and left this debris, we're over here right now, and a few months from now, we'll be passing through that. And then another year passes before we pass through it again. So we'll go through that comet's debris year after year after year. Okay? And that's what we call the meteor showers. When we do pass through that, you see more meteors than you do otherwise. So let's see. I think they have this on the, yeah, here we go. Here are the annual meteor showers. Okay, we're right now, August, 27th? Is that what we are now? So we just had Perseid, okay? We just missed the biggest one of the year. Next second biggest one of the year, okay? On the next big one will be Orionid, okay, and that will be on October the 22nd, about 15 meteors per hour. That's about one every 4 minutes. So if you really got some time on your hand, if it's a clear night, starry night, not too cold out there, go out there on October 22nd, and if you got time, take your blanket, something, lay down, just watch the star, and you'll probably see about one every 4 minutes, maybe see a meteor. Okay? And then happening the Taurids, November 1st, and then again on the 16th, where probably it went in and then came back out. You have to lay there about every 12 minutes to see maybe one. Okay? I'm not sure that's worth it in November. Okay? Up to you. November 17th, then Leonid, another once every 12 minutes or so. That's pretty chilly out there. But if you can do it on December 12th, just remember the day before my wife's birthday, okay? And she was born on a Friday too, by the way. Never mind, that's besides that. Okay? 55, almost one a minute. That would be worth it. If it's a clear night, it's called the Geminid meteor shower, December 12th, about 55. We'll be through with school by then, so you have to do this one on your own. But that would almost be worth it. If it's a clear night, go out there. You'll see almost one meteor per night. So that's meteors. When we pass through those tails of the where the comets has gone through and left debris, then we'll see these showers. Okay? Now, what makes a meteorite? A meteoroid is just a piece of stuff hanging around out there. So when we pass through and suck it into our atmosphere, that's when it becomes a meteor and it burns. Okay? That's what we're seeing. We're seeing it get so hot it glows. And most of the time it burns up. Okay? Completely. Okay? But every now and then it'll be big enough when it first enters that it won't all burn up. And if it does survive to strike the Earth's surface, that becomes a meteorite. Okay? And there are three basic kinds, with subdivisions. There's iron meteorites, which are mostly iron, which is most of what is the core of most of your planets. Okay? Iron. That's that ultimate result of fusion reactions. It gets down to iron and then doesn't get any more. So you have a lot of iron out there. That was whatever star exploded, nova, before our sun reformed its gases. Way back. Okay. Then you have the stony meteorites, And these are either chondrites or achondrites. Okay? Now that's all they say on the slide, but you can find this in your text, and I wanted you to know exactly where to look. Bottom of page 396, the first column. Okay? The stony meteorites, the second kind here, stony, okay, I lost my place, are further subdivided into two groups according to their structure. The chondrites, the first one here, and the achondrites. The chondrites have a structure of small spherical lumps of silicate materials or glass called chondrules, and that's why they call these chondrites, held together by a finely grained cement. The achondrites do not have the chondrules. Okay? And then the third type is the stony iron. They're a mix between stony and iron. Now, since we live in the area around Birmingham and Bessemer, and where all this industry has been, have y'all ever encountered, and I can't think exactly what it's called, I want to say slag, but that's not quite it. But it's when coal is heated, like forming coke or burned for utility purposes or whatever, there's always some debris in there, silicates, that basically gets melted in the intense heat of burning the coal, and then it re-solidifies in little bitty spheres. And then they have mounds of this stuff. I'm guessing there's a mound of it about Arkadelphia or so off the expressway there. I bet you that's what that is. I haven't been over there to see, but it's little spheres of material. That to me is what a chondrite is, a chondrule is. Those little spheres, something was heated really hot, silicates, and then reformed. When you heat sand very hot, and blow what you make. Glass, okay? These are glassy materials. These are silicates that have been heated, and the natural shape for them to get in are little spheres, because the sphere is the smallest that a certain mass can have the minimum surface area. It's a sphere. So they form these chondrules, which are the spheres. The chondrites have made up mostly of those chondrules, and the achondrites are made out of just chunks of things that are not in little spheres. All that talk, and what difference does it make? I don't know, but this is how they classify these meteors. Okay? Iron, stony iron, where they're stony, are either chondrites or achondrites, depending on whether they've got chondrules or they don't have chondrules. So that's meteors. Junk left from comets or asteroids that we run into. Okay. Before we run into it, they're meteoroids. When we run into it, they're meteors. If they strike the surface, they're meteorites. Okay. Now, this to me is almost a misleading picture. This is from the old text. The newer text is a little clearer. This is figure 1519 in your text. And the first of these is the stony meteorite. The smooth black surface, okay, was melted by compression in the atmosphere. In other words, the surface, as it got hot, it melted the surface, but then when it recooled, it formed this glassy kind of surface. Okay? The B is the iron meteorite. Now, to me, that looks stony and this looks iron, because I think of iron as being dark. But what makes that iron that color is it's been cut, polished, and etched with acid. So that's why it looks like this. That's what gives it the white color. Why wouldn't they show it before they did that so you would actually see what it looks like? Okay? I don't know. But they did it in the older text, they did it in this one. Okay? The pattern indicates the original material cooled from molten material over millions of years. Okay. Now, in that same figure in your book, figure 1519, it shows a time-delayed, time-lapse image of a meteor shower. And you just see those are just streaking across the sky. This is on page 396 in your text. They don't have a figure in your slide like that. But it's pretty amazing. You'll never see this, yes. Oh, I do need to take roll. Thank you for watching out for me. I get to running off at the yaw and forget to look. Luis is still here. Lexi is still here. Zarik is still here, right? Yeah. Okay. Brianna's still here, yep. CJ is still here. Ethan, still here. Amanda's still here. Jordan is still, well, yeah, there you are, okay. Still here. Jonah and Patrick are still here. Maurice is still here, right? Yep, there you are. Cameron, still here. Yep, right there. Derek, right there. Keegan, yeah. And Chris is still here. Page 1, perfect attendance. Way to go, folks. Page 2, Latricia. There you are. Okay. Evan is still here. Ian's still here mostly. Edward is here. We're trying to remember the name. Edward. Oh, is he already disappeared? Yeah. Oh, there you are. I see you now. You're hiding behind. Okay. Gotcha. Okay. Maya is still here. Okay, still missing Ken, right? Diamond is here, right here in front of me. Tamaya is still here. Ruben's still here. And Ryan is still here. I got you. All but one. Great attendance, people. Keep it up. Okay. Any questions? Meteors, meteorites, meteoroids, meteors? All right. Let's move now to 15.3, which is origin of the solar system. And this is next to the last, I think, subtopic, but it's a pretty short one in the text. We've already been hinting about it. Now, remind me from this point, 5:15 is the next thing to stop me at. Okay? Origin of the solar system. What did the prefix proto mean? Again? Sort of like preliminary. Before, pre. The protoplanet nebula model. What was it before they were planets? Okay? Well, they put this model in 3 stages. Now, this is just their best guesses, but there's lots of evidence that it's probably right. Stage A was the formation of the heavy elements as many earlier stars and supernovas compressed things into heavier and heavier materials. Okay? Now, this would have formed parts of the sun that's in here and parts of this disk out here. Okay? But everything was just sort of a glob at this point. Okay? The sun is probably protostar right now, trying to form up. May have formed, actually, but everything is still super hot. It's all vaporized pretty much because lots of reactions have gone on, and these things are just grouping together. So that's stage A. Stage B, well, continuing. Concentration in one region of space as the dust, gas, and chemical compounds. Okay, and this is the region. The sun in the center, and then these bands out here, probably pretty uniformly distributed, but beginning maybe to group or to clump. That's stage A. Now keep that in mind, because I think we're going, no, we got it. We keep the figure here. Stage B, the formation of large rotating nebula. The sun has now settled out into probably the actual star. May have still been protostar here, actual star here, but the rotating masses, now the sun is a hot ball of gases, right? That's all it is. Well, these have now clumped together large rotating nebula that go in these bands around here. Gravitational contraction pulls it together, the spin rate increases, and most of the mass concentrates in the protostar. So they're saying still a protostar, not yet a star yet, in the protostar. Most of the mass is there, but then you have masses out from there too. The remaining material forms in what they call the accretion disk. This is what it looked like before. This is what they call the accretion disk. And it groups together. Some places never failed to group, or did fail to group. They didn't quite group. That would be the asteroid belt. Material in the accretion disk begins clumping together in gravitationally connected pieces. But there's one out there, Jupiter. Well, it's going to be Jupiter. It sort of keeps the one inside of that, the asteroid belt, from ever clumping. Okay? That's what we think is happening. Yes? Say what?
Can you go back to stage A?
Oh, sure. Stage A. Sorry. I don't hear well, sorry. Nope, wrong way. Stage A. Let me get out of the way. You don't need anything. That's what you're doing. You got it? Okay. That was this stage. Just very beginning formation. Starting, sun's still a protostar, moving toward a star, not going back off again. It's going to be a star, and in the accretion disk, things do begin to clump there as well. Ready for C? Stage C, the protosun becomes a star. Now it's actually a star. It wasn't going back off from this, but it's now a star. The solar ignition flare-ups may have blown away the hydrogen and helium from the inner planets, because these flares happened and probably blew away the lighter materials, hydrogen and helium, and they are in the outer gas giants. We just don't have that much lone hydrogen or helium in the inner planets. Okay? They've been blown away. Okay? The protoplanets have heated, separating heavy and light minerals, the heavier sinking toward the cores, the lighter being near the surfaces. Okay? The larger bodies cooled more slowly, with the heavy materials settling out over longer times into central cores. Now, when they say settle out, some of the central cores are very, very hot, so they haven't necessarily solidified, but they have settled into those cores. Okay? And that pretty much then leaves what we've got now. So you can almost imagine there's Mercury, there's Venus, Earth just a little bit larger, Mars a little bit smaller. These are the four terrestrial, if that's what they're trying to represent. The relative distances are way off, like most of the illustrations are. And probably the sizes, especially Sun compared to those, the planets to each other, are probably not far from true. All right. So that's how we think we formed. Okay? Now, here are some ideas about the solar system. This, by the way, is 15.4, the last section. As I said, the other one was a fairly short section. Ideas about the solar system. Early in the game, we thought we were the center of the universe, as most teenagers do still. No, I didn't say that, did I? Okay. Because y'all are not far from it. Never mind, I won't even go there. Okay. That we were the center. Geocentric. Geo meaning earth, center of the universe. Okay? Attempt by the early Greek astronomers and philosophers were made to explain the observed motion of the sun, which seems to go around us, the stars, which seem to go around us, the moon, which actually did go around us, but quite differently from the sun and stars. That worked. Place the earth in the center of the orbits of the planets, which didn't work too well, because we're not there. Now, the exceptions of this model were explained by an Egyptian, I'm pretty sure he was, philosopher, early scientist named Ptolemy. I believe he was Egyptian. I don't think he was Greek, but they worked together. And he went to great extents to explain and form the model that explained this strange planetary motion, as far as he could tell. But after enough time went by, even his system began to break down. Inconsistencies in that system grew in number, became too complicated to explain, and it just became a mess. The roots of that model were based on church beliefs, but the Greeks were way before the church, okay? So actually the church picked up a lot of the sectarian beliefs, you know, and they got intermingled there. But we all thought we were the center of the universe, okay? Some still do, okay? Unfortunately. Now, then along came Copernicus, okay, the heliocentric model. Here was the idea of that Earth revolved around the sun, came from Copernicus. I already mentioned him earlier today. He was actually, if I'm not mistaken, was a monk. So he was part of the church, but his advantage was he was way out in the boonies, around where Poland is, not anywhere close to the center of learning, which would have been Rome. So he could have these thoughts and make these observations and discuss them, but he refused to publish them and left that to his disciple, you might say, who followed after him. And in fact, I don't even think he wanted him to publish it. I think he wanted him to destroy him. I can't remember that part exactly. The guy said this is too important, too good of material, so he published them after Copernicus' death. He did this about 1543. The inconsistencies with the geocentric model were explained really nicely by the heliocentric model. And everything going around the Earth, around the sun rather than the Earth, and now everything fell into place. So if the sun's in the center here, about where the Av is, okay, and this is the Earth at various times, you can see where you ran into problems. Mars being a real big problem. And this, who was it? After class talked about the regression, what was the word for it? Yeah, Mars in retrograde or Venus in retrograde. This is why this happened. So let's say here is our orbit, Earth. Here's Mars' orbit here. Now Mars further away moves more slowly, so it doesn't get as far. So let's say at time 1, here is Earth, there is Mars. Okay? So if you look from Earth and see Mars up here, that looks reasonable. Then here Earth is at 2, and there Mars is at 2. And Mars seems to be tracking across the sky quite nicely, okay, as it's supposed to. And then here is Earth at 3, and there's Mars at 3. Seems to be tracking along very regularly. Good boy, Mars, okay? And here at 4, here's where we are at 4, and there's where Mars is at 4. Seems to have sped up maybe a little bit, but it's still tracking along really nicely. But then when we get to 5, and this is quite a bit later, we're at 5, Mars is at 5. Mars is backed up on itself in retrograde. Okay? And then over here we are at 6. Here Mars is at 6, and it's backed up even further. And then when we get to here and Mars gets to there, suddenly Mars is going back almost like it should have been. And then 8, 9, and 10 just continue here. This is when it was in retrograde. It's going backwards across the sky. And Ptolemy and all the others, all the king's horses and all the king's men could not figure out why Mars was going backwards, okay? All the models, all the convoluted ways they had to explain it, they couldn't do it if the Earth was the center of the universe. But put the sun in the center, and it makes perfect sense. Perfect sense. Mars doesn't go around the sun, Earth. Neither does the sun or the stars or anything else. Certainly the other planets. They just seem to. Okay. So, Copernicus, I think, if I'm not mistaken, had the planets and most things moving in circular orbits. There were problems with that because we're not in circular orbits. Kepler's laws came along to further explain the heliocentric model, and here's the difference here. Kepler put us in elliptical orbits, which are slightly deviated, elongated circles. The sun is at one focus, and there's nothing at the other focus, and that's why sometimes we're closer to the sun, sometimes further away. Okay? So that's the Kepler's contribution. Now, Kepler observed this. I mean, he studied the measurements that had been made and came up with this as an empirical model. He could not explain why. Why would they do this? I don't know. So he went to this other sort of character that was around science at the time named Isaac Newton and said, can you come up with any reason why they would do this? This is what I've observed them doing, but I don't know what would cause this. So Newton thought about it for a while, and boy, when Newton thought, that was deep thought. Okay. He couldn't explain it, not with the math that he had, so he invented a brand new mathematics called the calculus. Now he could talk about instantaneous changes, not just average change, and with that, he was able to put together the mathematics that explain his laws of motion, which explain just about everything. Okay. Later we got into quantum mechanics and stuff like this. It brought out a few things that were a little bit in error about Newton's model. And in the future we're going to come into things that will explain stuff that we don't understand about the quantum mechanics. So all this stuff is evolving over time, and we're getting better and better ideas. But that's sort of the history of how we see ourselves and the universe around us. Okay. That is the last slide. There are a few more pictures. The figure 1522 shows Venus in retrograde. If you had a stationary Earth and Venus moving around it, Venus does weird things too. Ptolemaic system explained Venus, morning, evening star, blah, blah, blah. So there is a bit more done here than what our slide showed. The one on Mars was in our slideshow. And then Kepler's laws are kind of described in figure 1525 and 1526. And I won't go into great detail here, and then figure 1527. These almost outline Kepler's three laws. The first law says that a planet is not in circular orbit around the sun, but is in elliptical orbit. The sun's at one focus, the other. Not a single planet has that big of an ellipse, okay? Most of the time the foci are very close together, but they're always slightly elliptical. The second law said that and again this is greatly exaggerated, that the area outlined in a given time in passage is always equal. In the same time period, the area cut by that. Now this looks like this is way bigger than that, but if you count all that area here, they're the same. The perihelion is the closest approach to the sun. The aphelion is the farthest from the sun. I think of periscope on a submarine, you're really close. I think of this as almost like the Alps. Okay, this is just how I think of the word really far away. Okay. Now the third law is a really mathematical one that says the square of the period of the planet's orbit is proportional to the cube of its semi-major axis. Oh yeah, right. I would have followed that in no time. But look at what Kepler's third law, if you put this on log scale, both the distance and the period, look at here. Mercury, Venus, Earth, Mars, nothing. Think asteroid belt, Jupiter, Saturn, Uranus, and Neptune. They're almost evenly spaced out there, especially if you put in a planet there where the asteroid belt is. That would be almost evenly distributed. Earth and Mars a bit too close, and that other planet there, they're just about exactly evenly spaced on a log scale, which means they'd be doubling in distance on the regular scale, which is what they do. Okay. Pretty incredible that he did that empirically without knowing why, but just observing it right on the money. So, when you get to the end of the chapter, which we are, the person behind the science here is Gerard Peter Kuiper. They don't give an explanation of how you pronounce his name. I pronounce it Kuiper. I've heard it called Keeper or Kuiper or something like that.
How do you spell it?
Kuiper. Gerard is Gerard, and Peter is Peter. Okay. He was Dutch-born, but U.S. He did most of his work in the U.S. And the belt, the comet belt, was named after him. Pretty fascinating character. I would, again, this can give you ideas. This cannot be the source for your paper. You have to get the source from an outside source. This can give you lots of ideas about it. Okay? Yeah. Oh, okay. Now, there are several examples here that mostly deal with the mathematics, which basically based on the first half of the book, which we haven't covered yet, so I'll leave those off for now. But they're well worth a look so you can see what they're talking about. The summary here, I think, is fairly short, so don't count on the summary. I say this every chapter. I will say it every chapter. Nothing replaces reading the text. So try to get a copy of the book, e-copy, whatever, read the text, okay? Those little ones in the bookstore are not very expensive. Try to read that. Once you've read it, then the summary sort of focuses the main parts, but it doesn't do it all. Then the key terms are on page 403. They're listed alphabetically, but they do put the page numbers where they're first mentioned or described. Then I think the best thing to study for the test is applying the concepts that, in this case, 41 questions, a few fewer than we did in chapter 14, but about the same. The answers are given here, but it's well worth it to try to, you come up with your best guess of the answer before you look at theirs. Then there's 19 questions for thought. Again, a pretty good size number. 6 for further analysis. That's about normal. Invitation to inquiry. It's usually fun to look at. And then the parallel exercises are mostly the problem type, like in the examples, which we haven't focused on because we haven't, we really don't have the math background, first half of the book background for that. So the best thing to study in my mind is the applying the concepts, those 41 questions. You won't have 41 questions on your test. You'll just have a part of that. Okay. Too bad we don't have time to do the lab, but it's going to be close to a 2-hour lab. We don't have 2 hours left. We only have, about an hour before test time, right? Okay. So in that hour, do we need another break? What you think? Yes? A little louder. I can't. My hearing's so bad, I can't hear.
Finish the test early. Can we leave early?
Yeah, that's why I put it the last 30 minutes. So when you finish the test, otherwise you'd have to sit around until everybody else finishes and I go back to lecturing again. I didn't think you want to do that. Okay, so let's talk about what's coming up. Okay? The last 30 minutes today is the test. Most of you will finish well before 30 minutes. If you need more time, I'll be here till at least 6. I can stay later. Okay? So, that's today. Thursday, we will guarantee to have only 2 hours of material, 2 hours of lab, the lab from Chapter 15, and then 30 minutes of test for Chapter 15. So, guaranteed for Thursday. 2 hours of lecture, 2 hours of lab, 30 minutes of test. That would be Thursday.
We're taking another test on Thursday?
Yes, Chapter 15 test will be Thursday.
Okay.
And remember, you can have a formula and equation sheet, which you can have for this test today too, but now you got 2 days to work that one up. Okay? So
basically, we're going to have 2 tests per week.
I'm sorry?
Basically, we're going to have 2 tests per week.
1 to 2. We have 8 weeks and 9 chapters. So at least 1 week. This week we're going to have 2. Most weeks, see, for next week, for instance, once we finish chapter 16, we have a lab for 16, then we'll probably go to the planetarium if we can. So almost guarantee we're only going to have at most 1 test next week because there's just not time for it otherwise. So
Is the planetarium going to be during class time?
the what? No, planetarium, whenever we can schedule it to go there. And we have to drive
It
there.
will not be during class time.
It,
It won't be during class time.
well, it could be. It's whenever they can take us.
I got you.
So if it's the first part, we'll go there the first part. Usually that's what they want. And then we come back and have class. So that, on those days, we flip them. If they want us. Now, if he says, oh, I can't handle you at, say, the earliest we can get there is usually 2 o'clock. So if I can't take you at 2, but I can take you at 4, then we'll have class here and then leave and go down. Whatever works in his schedule, his or her, whoever it is now.
So are we going to take a small break right now? Or what are
We
about-
can.
What are we about
We're
to
going
do?
to start in
We're about to start another chapter?
we're going to start chapter 16.
Okay.
We need a break?
Yeah, we're going to take a break.
Yeah. Let's take a really quick 5 minutes or less break, and then we'll come back and start chapter 16.
Wait,
The wrong key.
so we don't.
What happened there?